Section 2.3, getting information from the graph of a function. So this section you're not going to be doing a lot of graphing. The graphs will typically be given already in the problem. You are just interpreting and evaluating graphs. So we have the 4 learning targets here. Evaluate. Now we've done a fair amount of evaluating functions in the previous 2 sections, but that's where we would take a number as an input and plug it into the equation of a function. We're going to do the same thing, but we use the graph. It's much quicker actually. Then we talk about domain and range. Remember, the domain is the set of all possible input or x values, and then the range is the set of all possible output or y values. And increasing and decreasing functions, and then talking about what are called local minimum and local maximum values. Okay, so to start off with, and again, the best way to approach watching these videos is not to simply watch. It's to pause, it's to write down, it's to ask questions, it's to fill in. So make sure that you're not just a passive bystander here, that you're taking an active part in this. So we have a function here, and this is the function f, and we don't know what the equation of the function is, but we do know that the graph has been given to us. And we need to find the value of the function when x equals 3. So what I mentioned, we've been doing this in the previous 2 sections. Typically what we would do is we would take the number 3 and plug it into some equation like 2 something squared minus 3 something, and we would just plug a 3 into that equation and evaluate it arithmetically, but we don't know what the equation is for this function. But essentially what we're doing when we're evaluating a function is we're just filling out an xy table. That's essentially what we're doing. When x equals 3, what is the y value? That's exactly what this is asking. When x equals 3, what's the y value? Well, we have it on the graph. When x equals 3, we have a y value of 3. So when x equals 3, y equals 3, or the function itself equals 3. So it's asking the same question, or a similar question here. What about when x equals 1? So when x equals 1, what does y equal? Well, here we have an x value of 1, so the y value there is 0. So f of 1 is equal to 0. So that's called evaluating a function using a graph. If I had asked for another one, f of negative 3, well, the input is negative 3, so that's our x value. What's the y value there? Well, we have an x value here of negative 3. The y value is 2, so f of negative 3 equals 2. Now, some of the questions are going to be asked in your homework go a little bit deeper than that now. So now I'm asking you to find all values of x for which f of x is equal to 0. Transferring to a graph, sometimes it's easier for students to think, all right, f of x is really the same thing as y values. So find all values of x that have y values of 0. That's essentially what this is asking. Find all points on the graph that would have y values of x and then give those x values. So, or have a y value of 0 rather. So here we have a y value of 0, and here we have a y value of 0. So we need to find all the x values associated with those y values of 0. So here we have a point 1, 0. Here we have a point negative 2, 0. So those are both points that have y values of 0. So the x values there are x equals 1 and x equals negative 2. Now the last question here, find all values of x for which f of x is less than 0. And again, f of x on a graph at least, you can think of those as y values. So we need to find points on the graph that have y values that are less than 0. And then once we find those points, what are the x values of those points? So on a graph, y values less than 0 means underneath the x-axis. Here we have the x-axis. Anything above the x-axis has y values greater than 0. Anything below the x-axis has y values less than 0. So this portion of the graph right here, this portion of the graph has y values that are less than 0. So what we need to do is locate all or state all of those x values. Now, rather than trying to locate individual points, because that's going to be impossible, between these 2 points there's an infinite number of x values. So what we do is what we talked about in section 2.1. We use interval notation between this x value and this x value. All of the x values between those 2 x values have y values that are less than 0. So let me get the right color, I apologize. So all of these points between -2 and 1 have y values that are less than 0. So all the values of x would be an interval with the left bound or the lowest number being -2 and the right bound or the upper bound or the highest number is +1. Now I just want to clarify, sometimes students mistake this notation as a point -2, 1. This is not a point on a graph. This is an interval of x values between x equals -2 and x equals 1. And notice I used parentheses, not brackets, because here I wanted it to be strictly less than 0 and not less than or equal to. If it had said find all values of x for which f of x is less than or equal to 0, then I would have used brackets. But since it was strictly less than, we use parentheses. So all the x values between -2 and 1, not including -2 and 1, all of those x values have y values that are less than 0. Okay, it's quite common to, in a section like this, to have to consider multiple functions or multiple graphs of multiple functions. So I've got 2 functions, function g and a function f. And first question is, which one is larger, f of -1 or g of -1? Meaning which function has a higher value with an x value of -1. So here we have the x value of -1, and I keep saying x value because remember, numbers inside the parenthesis are input or x values. So when x equals -1, which is bigger, the f function or the g function? And this right here has a higher value. F of -1, since that's the purple one here, f of -1 is equal to 2. G of -1 down here is equal to -1. So the larger value is f of -1. Okay, the next question, for which values of x does f of x equal g of x? And again, graphically speaking, f of x and g of x, these are just y values. So between the 2 functions, for which x values do the functions have the same y values? And if you focus right here, at this point, both functions have the same y value of 3 for a given input. So when x equals 2, y equals 3. So right there they have equal y values. And that also occurs right here at this point. At this point, the functions have equal y values, and I say equal y values because that's essentially what's being asked here. F of x equal to g of x, that's just a value of y that equals another value of y on a different function, because f of x and g of x are just y values. So what are the 2 points, since there's 2 intersection points, what are the 2 x values that coincide with those intersection points? It's here and here. So the x values would be x equals 2, and for x equals -3. For those 2 x values, the functions share the same y values. Now the next question, for which values of x is f of x greater than g of x? F of x greater than g of x on the graph means has higher y values or larger y values. So where on this illustration does the function f, which is here in purple, have higher y values or larger y values than g of x? And it happens right here. The function f of x along this interval has higher y values than the function g of x, which is down here. So, but the question asks specifically for what x values. So we wouldn't state that between this point on the graph and this point on the graph. We never state it that way. It says for which values of x is that true. So between this value of x and this value of x, which is this portion on the right side and this portion, so between those two x values, f of x has higher values than g of x. So between those two x values would be -3 and +2. So I would say between -3 and +2, and again I'm using parentheses as my grouping symbols and not brackets because it just said greater than, not greater than or equal to. If it had said greater than or equal to, I would have used brackets. And again, a point of confusion which I want to avoid, this is not the point on the graph 3, 2. This is an interval of x values from x equals -3 to x equals 2. So this is an interval, not a point on a graph. Okay, the next learning target is to determine the domain of a function and the range of a function given the graph and not the equation, which is actually quite easy compared to what we learned in section 2.1 when we had to find the domain of a function using its equation. Finding the domain when we have the graph is very, very easy, as is finding the range. So the domain is the set of all possible input values, and input values are x values. So when we're trying to find domain, we're looking along the x-axis, and any value that is in the domain would be producing a point on the graph. What I mean by that is, let's take the x value of -4. -4 doesn't have any point on the graph that has an x value of -4. There are no x values of -4 on the graph, so that means -4 isn't in the domain. It's not an input because it doesn't have an output. -3, however, is in the domain because when x equals -3, we have an output right here. We have a point -3, 2. So -3 is in the domain. -2 is in the domain because it has a point right here. -1 is in the domain. 0 is in the domain. X equals 1. So essentially what we're looking for is x values that are producing y values. So here from -3 to here +5. So any x value between -3 and +5 on the x-axis are producing y values, so those are in the domain. And so we have a left bound of -3 and we have a right bound or upper bound of +5. Now we need to decide on the grouping symbols. Do we use parentheses or do we use brackets? And the answer is, well, is -3 and +5, are they included in the domain or are they not included? Well, -3 is included in the domain because I have a point here, -3, 2. So -3 is in the domain because it has an output value. So I'm actually going to include -3 with a bracket and include +5 with a bracket also because I have a point of +5, 3. So 5 is in the domain because it produces an output of 3. So the grouping symbols would be parentheses. Now where that could change if this were a different problem is let's suppose that that last point there on the right, for example, came up to 5 but ended with an open circle. Well, if that's the case, if it ends there with an open circle, for example, then there is no point 5, 3. It doesn't exist. So 5 isn't in the domain in that case, and for that we would use a parenthesis rather than a bracket. So just some different variations there to be aware of, but since it was a closed circle to begin with, I'm going to finish it off how we started with a bracket. Now for the range, we do a similar exercise, except now we look on the y-axis. So the range is the set of all possible outputs, or the set of y values. So if we look along the y-axis, the highest value, or the highest number on the y-axis that's used as an output is 3. And the lowest number on the y-axis that's used as an output is -1. And so the lower bound for the range is -1. The upper bound for the range is 3. And again, we need to decide on the grouping symbols. And this point right here, for example, that's the point 4, 3. So since 3 is actually used as an output, it's included in the range with a bracket. And same thing with this point down here, that represents a point 1, -1. And since -1 is used as an actual output, it's also included in the range with a bracket, -1. So as a way to practice here, and by all means, when we're doing some of these practice problems, go ahead and pause it before I get into it to see if you can solve it on your own, and then check your answers against what I do here. So go ahead and pause it and try it. State the domain and range. Okay, so the domain along the x-axis, the x values that are producing outputs. There isn't anything to the left of -4 that we need to consider, because there's nothing to the left there. So we're going to consider -4 as our left bound, but there is no filled in circle there. It's an open circle, so there is actually no point -4, 1. That point doesn't exist on the graph, so -4 is not included in the domain. Since there's an open circle there, we would have a parenthesis. Now going to the right, notice there's an arrow there, not just a terminating point. There's an arrow, meaning that this graph goes all the way up and up and up to infinity. So I could continue going along this x-axis to x equals 6, to x equals 7, to x equals 8. Eventually I'd be able to come up here and hit the graph somewhere for any x value all the way out to positive infinity. So on the right side, the upper bound, or the right bound of this, is infinity, because it keeps going and going. So the domain is -4 to infinity. Now the range along the y-axis here, the smallest number, or the lowest value that's being used as an output, is -2. And since that output actually exists, there is a point 0, -2. -2 is used as an output, so it's included. And then the highest number, since again this graph continues to go up and up and up, I can go up to 6, I can go up to 7, I can go up to x equals 100 or y equals 100, and still have an output value there in the graph. So the upper bound of our range is positive infinity. And notice I always use a grouping symbol around infinity of a parenthesis. You never use a bracket around infinity, it's always a parenthesis. Okay, our next learning target, intervals on which a function is increasing, decreasing, or constant. So when we talk about where a function is increasing or decreasing, we're talking about where the x value, or rather where the y values are increasing or decreasing. So I've labeled a picture here. And the way that we typically read a graph is always from left to right. We read a graph similar to how we read, a textbook or a book. We always read from left to right. So if we're considering points along this function, we consider points moving from left to right, always left to right. So if we look at these points right here moving from left to right, the x values are getting larger, but the y values are getting smaller. So the x values are increasing, but the y values are decreasing. Because the y values are decreasing, we say that's a decreasing part of the graph. Now switching over to here though, the x values are still increasing. Anytime we move from left to right, the x values are always going to be increasing. But now the y values are increasing, so we say this is an increasing part of the graph because the y values are getting bigger as x is getting bigger. Now over here, if we're looking at points on this graph, moving from left to right, we now say that, okay, the x values are getting bigger because we're moving from left to right, but now the y values are also getting bigger. So this would be an increasing part of the graph. But now here the y values are getting smaller again, so that's a decreasing part of the graph. So we have a function here that's increasing and then it's decreasing because the y values are getting smaller. Over here on this picture, if we're looking at points traveling from left to right, again the x values are always increasing when you go to left to right, so the x values are increasing but the y values are decreasing, so this is a decreasing part of the graph. Here in this part of the graph, the x values are increasing but the y values are not increasing or decreasing, they're staying constant. So this is what's called a constant part of the graph. And then again here, the y values begin to increase again as x increases from left to right, and so this would be considered an increasing part of the graph. So what we try to identify in this part of the lesson are portions of the graph on which a function is increasing or decreasing or constant. So for example here, find all values of x for which the function is increasing, decreasing, or constant. And this is going to use interval notation like we did up above with domain and range. So first I'm going to identify the intervals where the function is increasing. Okay, if we look along this portion of the graph, the y values are increasing as the x values are increasing, but only up to a certain part, right here. The graph seems to switch, and I'm going to go ahead and draw a vertical line right here for just a moment. And then the graph is decreasing for a time because now the y values are getting smaller up to a certain point. So right there is another boundary or a switch in the graph. And then it starts to increase again from here to here. So let me do this in different colors. I'm going to do in red the portions of the graph that are increasing. So this is increasing. And then also here. And then let's use a different color here. This, that's not what I wanted. Let's try that again. This portion of the graph, since the y values are getting smaller, we would say that's decreasing. Now the mistake students make often is trying to describe where this is happening by giving it from a point on a graph to another point on a graph, but we never describe it this way. It's only values of x. So we use intervals of x values like we did with domain and range. So this interval, for example, where this portion of the graph, what are the x values contained in that portion of the graph? So the right bound would be all the way up here to -1, and the left bound on this x-axis would be all the way to negative infinity. So the increasing part for that would be from negative infinity all the way up here to this boundary line right here. That's where the graph switches from increase to decrease, excuse me. And that boundary of where it switches is x equals -1. And this is just something you need to remember when we're talking about increasing and decreasing intervals, especially where it switches from one to the other. It's always a parenthesis. So it's increasing from negative infinity to -1. And then it starts to increase again right here on that portion of the graph. And so it switches at this boundary line, which was -2, or rather +2. And this is not an arrow, it's a terminating point. So it stops when x equals 4. So it's increasing between the x values of 2 and 4. So the intervals of increase are from x equals -1 to x equals -infinity to x equals -1, and then again from x equals 2 to x equals 4. Those are the intervals of increase. Now the intervals where the function is decreasing, the x values for which the function is decreasing, is right here on this portion of the graph, but we never state from a point on the graph to a point on the graph. It's always just x values. So these x values here and here would be between -1 and +2. So the graph is decreasing using x values between -1 and +2. So that's how we state, and that's how we answer these questions. Find out all values of x for which a function is increasing, decreasing. We didn't have any intervals on which the function is constant. There weren't any portions of the graph where the graph had a slope of 0. Now, this leads right into our last learning target, and it's very quick. Local maximums and local minimum values. So what I've done is just copy the same graph down here that we just had. We already determined intervals of increase and decrease. This was an increasing interval, and then we had a decreasing interval back to an increasing interval. So local minimums and local maximums occur when a graph switches from increasing to decreasing or decreasing to increasing. So let me back up here and try to explain this again. Local maximum and local minimum values are different than what are called absolute maximum values and absolute minimum values. And let me try to explain that difference. This point right here, well, no, let me use a different point. This point right here, this is not the lowest point on the graph. This graph goes all the way down to -infinity, so there isn't a quote-unquote lowest point on a graph. That would be called the absolute minimum. If I continue to go down and down and down, I could always find another point that's lower than another point I just found. So there is no absolute minimum value. This point up here, this is the highest point on the entire function. So that's what's known as an absolute maximum value. It does have an absolute maximum value. This one does not have an absolute minimum value. But we're not talking about absolutes. We're talking about local minimums and local maximums. So back to the point I highlighted first. This point right here. No, it's not the lowest point on the graph. But if we consider a small neighborhood of the function, a neighborhood means a very small portion around that point. So if I consider just that portion of the graph, then that is the lowest point on that portion of the graph. So that's what's known as a local minimum. Local minimums only occur, by the way, when a function switches from decreasing to increasing. A local minimum will occur when a function switches from decreasing to increasing. Okay. Now this point here, even though we just identified it a few minutes ago as an absolute maximum, it's also what's known as a local maximum, because in this neighborhood or that area of the function, that is the overall highest point in that neighborhood or that area of the function. So it's called a local maximum also, and incidentally, a local maximum only occurs when a function switches from increasing to decreasing. So a function has to be switching from increasing or decreasing to produce a local maximum, and it has to be switching from decreasing to increasing to produce a local minimum. So to find the local minimum and maximum values, here's how you state it. There's a local maximum of and then you state the y value. There's a local maximum of y equals 4, or you could just say a local maximum of 4 when x equals, let's see, when x equals -1 right there. Whoops. Let's use the right pen. When x equals -1. There's a local minimum of, and we give the y value there, which is -1, when x equals 2. Now it is possible for a graph or a function to have several local maximums or several local minimums. Looks like I did not include that example. I had intended to, I apologize. So let's go ahead and add it right now. And this is going to get a little messy. Again, I apologize. Okay, so we have a graph here. Let's say this is the function f. Find all local minimum values and find all local maximum values. Okay. Now, one thing I want to point out right at the beginning, a common mistake students make is looking at a point like this, for example, saying, hey, that's a high point on the graph. That is actually the highest point on the graph, so that must be a local maximum, right? The answer is no. Remember, a local maximum only occurs when a function switches from increasing to decreasing. So at that point, the function's increasing for sure, but it's not switching to decreasing, so that is not a local maximum right there. So let's identify some intervals. Here we have an interval of increase. Here we have an interval of increase. Here we have an interval of decrease. Here we have an interval of decrease. So the graph is switching here from decreasing to increasing, so that's a local minimum. We also have another interval right here. The function is switching from decreasing to increasing, so that's also a local minimum. So there's two of them. So we would say local minimum value of the first one here was the y value is 0. So a local minimum of 0 when x equals 1. There's also a local minimum of right here, that's a y value of -1. So a local minimum of -1 when x equals 2. So we have two local minimum values. Now here we have a local maximum value because the function is switching from increasing to decreasing. So here we have a local max. So there's a local max of 2 when x equals 0. Okay, so quick wrap up of what we've talked about in this lesson. We talked about evaluating a function. So given the graph of a function, evaluating f of 3, well, 3 is the x value, so what you're trying to find is the y value. So that's evaluating a function. We practiced looking at several functions and comparing two different functions on the same graph. And then we're looking at y values, but then the answers we're giving are intervals of x values. Talked about domain and range. Domain and range, domain is x values along the x-axis, range is y values along the y-axis. And just pay attention, a common mistake when doing domain and range is having the incorrect grouping symbols. Make sure that you either have brackets or parentheses correctly. And then we talked about intervals of increase and decrease. And functions never, you don't state these as stating it from a point on a graph to another point on a graph. It's always intervals of x values when we're stating intervals of increase and decrease. And that does it for 2.3.